angular velocity of links. So let us say this link is rotating counterclockwise like this. So the angular velocity of this link is given like this. So now the velocity vector for this, so the velocity vector at point A, okay, will be perpendicular to the link, and it will be like this. So this is the velocity of point A. So this angle will be 90 degrees. So it doesn't mean that the velocity vector is showing downward direction, so it is not clockwise rotation. So the link is not rotating, okay? Okay, in this case the link is rotating clockwise, okay? So if the link is rotating counterclockwise, okay? So the same velocity vector, okay? So the same velocity vector will be in the opposite direction. So it depends, okay? Now we need to see whether the velocity A is negative or positive, okay? So you can measure with respect to the local coordinate system. So local coordinate system means now you can shift your coordinate axis to point A, okay? So you can consider this as your local coordinate axis X and Y. So you can measure with respect to the local coordinate axis the angles, so velocity vector angles. But based on the velocity vector angles, you cannot fix the orientation of the link, so the angular velocity of the link. So the direction, whether it is clockwise or counterclockwise. So you need to always look into the length of the link, the angle of the link. So that is important. Okay, so what you should know is that depending on the orientation of the link, the angular velocities, okay, the direction of angular velocities, the velocity vector's direction will be there. Okay. So we use the velocity vector's directions whether they are positive or negative. So to fix the angular velocities of the links, okay. So considering that the velocities of the links, okay, the velocities are perpendicular to the links. Okay, so velocities will be always perpendicular to the links and the given orientation. Alright. So next I move on to the simple 4-bar linkage mechanism. So this was done. So consider the point A, let us say point B. Okay. So this is, let us say, the position of point A. So this is position of point B. So when we draw this, the position of point B from A. So many times we have seen this. This is the basis of the velocity analysis or acceleration analysis. So from this we can write, okay, the position vector B. The position vector B can be written as the position vector A okay, plus the position vector B to A. So this is a vector equation. Now if you take the derivatives of this, you can also write similarly the velocity vector B is equal into the velocity vector A plus the velocity vector B to A. Okay, so similarly based on this we can also take the derivative both sides, so you can write acceleration of B is acceleration of A plus acceleration of B to A. Okay, so this is, we are linking point A and B. So this is only a simple link. Okay, only a single link. Now, let us say this is a link. So we call this as O2A. So I give angular velocity omega 2. So can you tell me what is the velocity of point A? So we know that it is simply O2A into omega 2. So why? Because the point A, the instantaneous center is O2. Okay? So the instantaneous center for point A is O2. Now, I take another point on the link. Now let us say I have a point on the link here. Okay? I call the point C. So what is the velocity of this point C? So can you calculate the velocity of the point C? So what will be the velocity of point C? So for that matter, any point on the link other than point A. So any point on the link, you can simply find the distance from the instantaneous center O2C, then you multiply with angular velocity. So any point on the link, we can calculate the velocity if you know the distance from its instantaneous center or its origin. Okay, so any point on the link, we can know the velocity. So why? Because for any point on the link, the instantaneous center is O2. Okay, so we have seen in the last sessions, and you must have completed your assignment 1. So we have done velocity by 2 methods, velocity polygon method and velocities by instantaneous centers. Okay, so what now I do is, what we have done in the last sessions are basically simpler examples, and mainly I wanted to drive you towards your assignment. Okay, and yeah. So now today's session we'll try to revise the concepts, and also we look into a bit more deeper aspects of velocity analysis, acceleration analysis, and I'll go to your assignment 2. First question of your assignment 2, that is analytical calculations. Now, for assignment 1, you have done the graphical position analysis, you have done the velocity polygon or relative velocity analysis, then you have done the acceleration analysis, and also you have done velocity analysis by IC's method. Okay, so for assignment 2, again there are 4 parts. So the first part is you are going to do the velocity analysis, acceleration analysis by analytical method. So that means by deriving the equations and using the equations and calculating the same velocities, and you can always compare the analytical calculations with your graphical calculations. Okay, so assignment 2, the first part is analytical calculations. So normally I have uploaded the file already, so probably you could have seen that. All the required equations are there. So only thing is use those equations and do your calculations, because for your mechanism, your theta 3, theta 4, all the values will be different, right? So you can still, everybody can use those equations, all of you can use the equations, and you can do your analytical calculations, and you can always compare your values with your previously calculated values from graphical analysis. So generally there will be a very good correlation within 2% error. Okay, so even if you don't get the values, please don't change, you just report as it is. Okay, so that is required. So you don't lose many marks even if you do a wrong thing, but you need to make sure that you applied, you have used the given values to you. Alright, so next we move on to the relative velocity analysis. So as you can see, the relative velocity analysis is, we have just seen the equation, right? Velocity v is equal to velocity a plus velocity b to a. So the velocity at one point can be expressed as, you can see, can be expressed as the velocity of another point. That is what we are seeing. Okay, now this is a 4-bar linkage mechanism. Just you feel comfortable, get acquainted with this. So the first one is okay, O to A, right? So angular velocity omega 2 is given. Okay, so counterclockwise theta 2 is given. Then you have plotted the mechanism to scale and you got your theta 4 and theta 3. Right? So theta 3 is measured with respect to a local coordinate axis. So theta 4 is again measured with a local coordinate axis. Okay? So the global coordinate axis starts with the O2. Okay, it is fixed. O2 is fixed. Right? So this RA is the position of the point A. So this is a vector. Okay, I think I switch on that. Okay, so this is the position of B from A. Okay, so this is a vector. So R A bar is a vector, R B bar. So this is the position of this B bar. So now the velocity, relative velocity equation. So what we are writing? So we are writing velocity of B. So we know that this is the angular velocity of link 2. Omega 2 is given. Okay, so the velocity B will be perpendicular to the link 4. So this is link 4. So velocity B, the direction you will be knowing. So the direction of velocity B will be perpendicular to the link 4. So then we can write this is equal into velocity A. So velocity A is again perpendicular to link 2. So in this case, we can fix the direction of velocity A because we know the angular velocity, the link angular velocity is given. So as it is counterclockwise, so you can see the velocity A, the direction. Okay, then we can write velocity B to A. So this is the relative velocity equation. Velocity B is velocity A plus velocity B to A. So B to A will be perpendicular to the link AB. Okay, so this is, we have completed. Now velocity B is velocity A plus velocity B to A. Now here we are linking 2 points A and B. Okay, so what is that we know? We know completely the magnitude and direction of velocity A. And we know the direction of velocity B and the direction of velocity B to A. So from these two, then now all the directions are shown here. Okay, so the velocity directions based on I think this is not connected. Is it okay without this? Change, right? But in the past, it is to work. see maybe a bit later. Okay, so we can draw the velocity vectors like this here. So now we know complete information of velocity A, both magnitude and direction. Okay, and we know the direction of velocity B. So velocity B will be simply perpendicular to the link form. Okay, it may be as shown here or it may be downwards. So similarly, velocity BA will be only perpendicular to the link AB, and it can be upwards or downwards. Okay. So now using this information, we will be able to plot the velocity polygons, and then we can find the two unknown quantities. Okay. So for example, the direction and magnitude of velocity A is known. How we know? Because omega 2 is given. So therefore, VA is O2A into omega 2. Then the magnitude of the direction of VA will be theta 2 plus 90 degrees, or so we can find out depending on the angular velocity of link 2. Okay, so then the direction of the B and B to A we know. The velocity vector directions of point B and B to A we know. So based on these two, we can plot the mechanisms to scale. Now let us say the mechanism, 4-bar mechanism is given as shown here. Okay, so try to follow carefully. Here point A, point B. Okay, so then there is point C. So point C is on link 3. Point C is on link 3. Alright, so then angular velocity of link 2 is given. Angular velocity omega 2 is given. Okay, so now we are linking point A and point B. Then we can write velocity B should equal to velocity A plus velocity B to B. Okay, so we can write, then we choose an appropriate scale. Now this is your origin. So you have just taken the scale as 1 mm is 5, okay, mm per second. So the velocity scale is 1 unit is 5 mm per second. So it depends, okay, based on your whims and fancy. So you can choose. Omega 2 is given 10 radians, O2A is given 30 mm. So what will be the velocity A? Magnitude. So magnitude will be is 30 into 10. So you will get 300 mm per second. So what will be the direction of velocity A? So velocity A will be perpendicular, since the link is moving like this. Okay, so it will be perpendicular like this. Okay, so we can see in the next slide. So velocity A will be perpendicular to the link. So you know the direction of this velocity A, both magnitude. So the magnitude will be 300 mm per second. So the magnitude of this velocity. Okay. Then the direction. So direction, if you want to do this on piece of paper, okay, you can use your set squares. Okay, you can use your set squares. You know the direction, right? So you just shift your set square to the point O. Okay, if you are plotting the velocity polygon on the same graph, on the same paper, okay, once you plot this direction on your graphical position, then you can just shift the same direction to fix. Otherwise, you can measure this angle and you start putting the same angle and draw the magnitude 300 mm apart based on your scale. So you can use whichever way you want to draw the velocity polygons. So now you can see the same velocity vector, the direction is maintained, the magnitude is now 300 mm per second. Okay, so now what is the equation? So velocity A we have plotted. Now we need to add to the velocity A, that means from the tip of this, velocity B to A. Now velocity B to A, we only know the direction. So we know that B to A velocity will be perpendicular to AB. B to A velocity will be perpendicular to AB. So now it can be upwards or it can be downwards. So now we need to add this to point A. Okay, so what you do, so you can again use your set squares, okay, just move the same thing to point A. You plot the same direction at the tip of point A. So you only know the direction, but you don't know exactly whether it is upwards or downwards and the magnitude of the velocity. Okay, but now we have drawn this VA, we have drawn VBA, we have drawn. Okay, so now we need to draw velocity B. Okay, now velocity B will be perpendicular to the link 4. Okay, so this is the direction of velocity B. So now you are bringing the same thing to the point origin here. Okay, so that is the dashed line which you can see is the direction of velocity B. Guys, is that clear? So this is the basis of your relative velocity equations. Now the intersection point you can see. So once you know the intersection point, now look at this velocity vector. So velocity A plus velocity B to A. So now the velocity B to A will be upwards or downwards? B to A. So this vector now plus this vector. So that means velocity B to A will show downward sideways. Now obviously this vector plus this vector should equal to velocity B. So that means the direction of velocity B we can trace. Okay, so we can complete this velocity polygon. So we know now the magnitude. So this is the direction of velocity B. Okay, and you can know them from your plot. Okay, you can measure this distance and whatever the scale factor. I have uploaded all this file so you can download. So please note that all the files starting from day 1 to today's are available on Canvas. Okay, so now you know velocity B. So the magnitude of velocity B you can measure from your drawing and multiply with your scale factor. So in this case the scale factor is 500 per second. Okay, so it is multiplied and the orientation of this now how do you measure? So it is given as 15.2 degrees. Okay, so you are choosing your coordinate axis. So this is your coordinate axis starting from point O. Okay, so with reference to this you measure that is about 15 degrees. Okay, so that is the direction of velocity B. So next we find out so now you know the magnitude and direction of velocity B. Okay, so next we fix this B to A, okay, direction. Now you measure the magnitude of VBA, so then multiply with the scale factor whatever it is, then you know the magnitude of velocity B to A. Okay, and you can also find out, if you want, you can find out the orientation of this velocity B to A, the direction. So fix a local coordinate axis here, okay, x, y, local coordinate. Then with respect to that you can measure velocity B to A. Okay. Now once you know velocity B to A, then you can calculate the direction of angular velocity of link 3. Because we know now velocity B to A, if you divide this with the length of the link AB, you will get the angular velocity. Okay. Now to do this, we will take the magnitude of velocity B to A. So we don't bother whether it is positive or negative. We only take the magnitude. Okay. So once we take the magnitude, you know the magnitude of the link 3 angular velocity. But whether it is clockwise or counterclockwise, now you can decide based on here. Because if it is counterclockwise, so this vector should be projected upwards. Okay, so that means this, since velocity dA is downwards, so angular velocity of the link at this angle is clockwise. Okay, so because of this. Okay, so you are only taking the magnitude of velocity dt. So this is true for any velocity. So whenever you are calculating angular velocity, we only take the magnitudes. Is that clear? So now we know the A, B, so we know all the velocities. So then you can calculate the angular velocity of link 4. Okay? So velocity B over the length of link 4. Okay? 90 mm is given, so you know the magnitude. Now velocity B, as you can see, is upwards and positive. Okay? So that means now you imagine the link velocity is as shown here, right? So that means this link is rotating clockwise. Link 4 is also rotating clockwise as shown here. Because the velocity vector is perpendicular to the link. Is that clear? So now this is how you will draw the velocity polygon for 2 points. Point A, we know complete information. So now we linking point B. Point A and point B is linked. So we can use the expression VB is VA plus VBA. Then we plot the velocities vectors, then we complete the polygon, then we measure the length of the velocity vectors, then from there we can calculate the angular velocities of link 3 and link 4. Okay, so now the point is, what will be the velocity of the point C? Because point C is on link 3. So you know the distances AC and of course you know the distances CB. Okay, so to know now the velocity of another point on a link, so we can now link A to C or you can link B to C. So in this case we are linking velocities of A and C. So in the earlier we are linked A and B. So now we can link A and C. We can write velocity C is equal to velocity A plus velocity C to A. So velocity C to A we know because angular velocity of link 3 we know. Okay, and you can multiply with this AC to find out the velocity vector CA. So that means the magnitude of velocity vector CA we will be able to know. Okay. So now you can see here, you can also link the point C and B also. Okay, so you can link C to A, then the direction of this will be perpendicular to this CA. Okay, so now on the same velocity polygon, so guys you need to follow this carefully. So on the same velocity polygon, so now you are linking, this is A, right? So we know the direction of C to A. Okay, so from the tip of this we draw the direction of velocity C to A. So from the tip of A we draw the direction vector CA. Okay, so we know CA will be perpendicular to this. Okay, so just again use your set square, you can just shift and you can draw the line. Okay, so we can also write now C and B. If you link C and B, because we know complete information of B, we know velocity B, right? So we can also write velocity C is equal to velocity B plus velocity C to B. Okay, so we can also write velocity C is velocity B plus velocity C to B. So now we have drawn the velocity CA vector from the tip of A. So now similarly we try to draw the velocity vector from tip of B. So what will be the direction of CB? So the direction of C the next one. Okay, So the direction of CB will be as shown here, perpendicular to CB. Okay, so direction of CB will be perpendicular to the link CB. Okay, so the next we draw the same direction passing through from point B. Okay, you draw this dotted line from the tip of point B. So now these two dotted line vectors in red, so they intersect at this point, right? So now we can fix the point C. Okay, draw a velocity vector to the point C. So the magnitude of this will give you the magnitude of velocity. So measure the distance, multiply with the scale factor, that gives velocity C. Okay, so the direction also you can measure using a local coordinate system. Okay, so the direction, now for that point, now you can see this is the link AB. Okay, you can see ACB. So similarly, you can also see here in blue ACB. Now, can you see any similarity between the triangles here? So here the triangle ACB is the geometric triangle based on the dimensions of the links. Now here the ACB triangle is the velocity vectors. Velocity vector triangle. Now, is there any difference in the shapes? So now imagine this link is rotated 90 degrees. So if you imagine the link, the triangle ACB is rotated 90 degrees, so you will get the same ACB velocity triangle. So this velocity triangle is called the velocity image of the link ACB. So velocity image of the link ACB. Okay. So magnitude, velocity, and orientation you can calculate. So for that point, if you want to find out at any point on link 3, you want to find velocities. Now from this velocity image, you can easily calculate. So for example, from A, you want to find out at this point what will be the velocity, let us say. Okay? So you can just draw a velocity vector to that point on the image, and that gives you velocity of this point. So on any point on link 3, you will be able to measure velocities using this velocity image. Okay, so now we talk about the velocity image. Now what you see here is CED, as you can see here, CED. So this is the geometric link. Okay, so now when you do the velocities, so the same geometric link, you can see a 90 degrees rotation here. Now this becomes your velocity image. Now you want to point, you want to know the velocity at point D. So just plot a velocity vector to the point D on this velocity image. Okay. So the velocity image you can similarly draw as we have drawn in the previous example. So in the same way, any link, okay, you can draw the velocity image. Now, any point on the link, you can find out the velocities from the velocity image easily. So each link in a mechanism has an image in the velocity polygon. So this is your velocity polygon, and this is your link. So the link has an image here. Okay. So using the velocity imaging technique, it is possible to find out velocities on any point on the links. Okay, so in this case, the velocity of D is shown here. So let us say you want to find the velocity on CE at this point, let us say. So you want to find velocity at a point on CE. Okay, so just draw this velocity vector to that point. Okay, let us say you want to find out the velocity at this point. Okay. On CD, you just draw, locate this point and draw the velocity vector to that point. So measure the direction and magnitude.
So this one is what you did just now, right? Everything is just perpendicular.
We have done based on the same way right here. So first we know the velocities, right? This polygon. Okay. So now we need to find out the velocities at this point C. So first we link A and C. Okay. So the direction of velocity C to A will be perpendicular to this, right? So now you are linking A and C. Okay. So from the tip of A, you draw the direction of velocity CA. So this dotted red line. So that is you are linking velocity C as velocity A. So velocity A plus velocity CA. Velocity CA, we only know the direction. Okay. So therefore we draw this dotted line. So now we can also link this to point B. Then you can write velocity C is equal to velocity B. So velocity B plus velocity CB. So now we need to know the direction of velocity CB. So the direction of CB will be as shown here, perpendicular to the link CB. Okay. So now from the tip of B, so we draw the same dotted line. So the same direction. So now we draw same dotted line. So you can see the same dotted line. Now the intersection point we identify. Okay. Then we can see this as the velocity image. Now ACB is the velocity image of the link ACB. So this is how we plot. So this is just to extend our knowledge. Now we can calculate or find out the velocities on any point of the link. So there is no need, suppose say you have one point here, another point here, another point here. So there is no need to plot velocity polygons again. So using the velocity image, now any point on the link you can find out the velocities. So this is mainly theoretical interest. This is just to tell you that using velocities, we can draw velocity polygons, and velocity polygons will have resemblance to the links. So the linkage information can be used as velocity imaging. So you can see. So velocity images you can now identify. So the advantage is any point on the link can be calculated using the velocity images. Okay. So once the velocity of 2 points on a link is determined, the velocity of any other point that sits on the link can be readily found. So you can find out the velocity of any point on the link. So the 2 points can be used as the base of the velocity image. So the shape of that link can be scaled and constructed on the velocity problem. So depending on the lengths of the links, so we can use the velocity images and we can find out velocities of any points on the links. Okay, so is that clear, the concept of velocity image? Okay, so once the velocity image is known, now there will be instances where now a point will be representing two links. Okay, so now for example, this is the coincident points on different links. So this normally occurs when you're dealing with slides, pistons, cams, and other systems. Now 2 points on different links momentarily occupy the same point. Now for example, this is link 4. Okay, so link 3 is the slider, and this is connected to link 3. Okay, now at this point now the point corresponds to link 2, link 3 and also link 4. Okay, so that means link 3 is now common to link 2 and link 4. And each has a different absolute velocity and therefore relative velocities do exist. Now in such cases, now the link 3 is common to both link 2 and link 4 and instance, and link 3 has its own velocity. So therefore there will be a relative velocity between link 2 and link 3 and also link 3 and link 4. So this is a common feature for sliders. So now let us look at this example. So this example, the angular velocity is given clockwise. Okay, the velocity, the length of the link O2B is given, and O4B4, the length is given. We were asked to calculate velocity B4. Okay, and angular velocity of link 4 and velocity of point C. So point C is on link 4. Okay, so omega 2 is given. Okay, this is clockwise and 10 radians. So therefore we know velocity of point B. So we know velocity of point B, both magnitude and direction we know. So velocity of point B on link 2. So that will be 10 into 75. Okay. So you know the direction. Now this is clockwise. Okay. So therefore the velocity is perpendicular to the link at this position. Okay. And we are taking the scale for velocity polygons. Now the same direction is plotted, velocity V2. So this is the velocity of the point B on link 2. So velocity of the point B on link 2. So we can now link B2 and B4. Okay. So the velocity of the point B on link 2 and link 4. Okay, so we write the relative velocity equation. So the relative velocity equation is velocity of point B on link 2 is equal to velocity of point B on link 4 plus the relative velocity. Plus the relative velocity. So we can also write similar equation. So linking point B on link 4 and link 2. So we can also write velocity of B on link 4 is equal to velocity of B on link 2 and the relative velocity of B2, B4. Okay, so we can write these two equations. So now we know the velocity B2 both magnitude and direction. Right? So velocity of B2 both magnitude and direction, so you can plot this. So that is 750 mm per second. So multiply angular velocity given, then the length of link 2 is given. So the direction will be perpendicular to the link O2B. So it is plotted. So we have plotted velocity of point B on link 2. So next we need to plot the velocity of B on link 4. So velocity of B on link 4. So here the point B on link 4, because the slider is sliding on link 4. So therefore the direction will be in the direction of the link. Okay. So it is sliding downwards and upwards on the link 4. So point B will have velocity, okay, on the link 4. So B2, velocity of B2, B4 will be parallel to the link O4, B4. So from the tip of velocity B, so we can draw the direction of B2, B4. Okay, so B2, B4, the relative velocity will be in the along the direction of the link 4. So next velocity V4. So the direction of velocity V4 will be perpendicular to the link 4. The direction is as shown. Okay. So now from the origin we draw the velocity V4 direction. So velocity of point B with respect to link 4. Okay. So with these two now dotted lines, red dotted lines, now you can fix it. Okay. Then you can measure the direction of velocity V4, both magnitude and direction. So as measured from the figure, it is 30.33, then the scale factor, then you know the direction of velocity, magnitude of velocity of point B on link 4, 383 mm per second. And the orientation again you can measure using a local coordinate system. So we just establish a local coordinate axis here, then you can measure the direction of velocity V4. Okay, so once you know velocity V4, then you can calculate the angular velocity of link 4. So angular velocity of link 4 will be velocity of V4 over the length of the link. So if you do this, then you will get the magnitude as 5.63 radians per second. And as you see, based on the direction of velocity V4, you can say that the angular velocity of the link 4 will be clockwise. Okay, so next we can link C and B4, point C and B4, because you can see this is the point C here. So now you can link point C and B4. So you can write velocity C is velocity B on link 4 plus the relative velocity. Okay. So we can now draw the direction of velocity B, velocity C from B4. Okay. So velocity of C from link 4. So this is the direction of velocity C, the dotted lines. You can follow the, okay. So you are drawing this from the tip of VB4. Okay. So this is VB4. We know already we plotted this. Then you are adding this velocity, relative velocity C to B4. This direction. Okay. So next we can draw the direction of B to B4. So B to B4 will be again in the direction of the link. So B to B4 we have drawn. Now we are drawing the direction of velocity C to O4. Okay. So this will be perpendicular to the link C4 as shown in the dotted line here. So this you are plotting direction of B, C, B4. Okay. So this is the link. So this is the direction of velocity C, because you are referring to origin. So this is the velocity C vector. Okay. So this is velocity C to O4 means velocity C. So this is the origin fixed. So now you fix, okay, then you can measure the velocity C, then this is the unknown. Okay, so you can measure the velocity C vector, then you know the orientation also. Okay, so like this, by doing the velocity analysis by linking points. Okay, so now we have points where the point is common to two links. Okay, so this example is slightly different because we are dealing with a point B, which is connected to link 2 and also link 3, and this B3 is sliding along link 4. Okay, So you can see the velocity of point B on link 2 and velocity of B on link 4 will be having a relative velocities. Okay. So we can write now link B4 to B2 and okay, so we can link BC to B4. Okay, so we can link B4 to B2 as shown here. Okay, then we can link B4 to B2, B4. Okay, always we start for 2 points. We write the relative velocity equation, we draw the polygons, we try to find out all the unknowns. So mainly the directions and magnitudes. Okay. So once we have the complete information for 2 points, then we can connect these 2 points to any other point on the link. Okay. So we can draw again the relative velocity equations and again we draw the polygons. But when you draw the polygons, now what happens? Whatever the velocity polygon you have drawn, we can make use of the same velocity polygon. Okay, so we can. So this velocity imaging will be built on the original B2, B4. Okay, so the polygon you can see in black. Okay, then you can see the polygons drawn to the original velocity polygon for other point. Now mainly we want to find out the direction of magnitude and direction of the points. Okay, so you can use the velocity polygon to construct polygons on the same velocity polygon for any other points on the mechanism. Okay, so this type of analysis may be required for you in the exams. Not class test or class test we talk later. So when I say exam, end of term exam. Okay, so end of term exam, normally the velocity analysis will be given for 6-bar linkage mechanism. Okay, and for the exam, because now we are doing supervised exam, Dr. Firoz Alam, Professor Firoz will be coming for the pre-exam workshop. So please don't miss a single session. Okay, so he will be guiding you for a 6-bar linkage mechanism, very similar to the questions that will be asked in the exam. Okay, so just don't miss the pre-exam. All right. So this is about the velocity analysis. Now with this, and if you have done your assignment question, then I think concept-wise you must be clear. Okay, so it is the idea is very simple, but when you plot this on paper, okay, then it requires some practice. So it requires using your geometric box, effectively. So without practice, it's difficult, exactly. So we need to practice yourself. Okay. So otherwise, all the 3 hours you will not be able to do anything meaningful. Okay, this is another example. I just did this. It is very similar to the same one. So the next we move on to the IC's method. Do you guys have any questions? Because everything centers around that equation which we write. Velocity v is velocity a plus velocity v. So that is the relative velocity. So we can't use the calculations because these are vectors. You can't split into components and do the analytical solution because you will be asked to do using graphical analysis in the exam. Any doubts or any questions? No? Alright, then we move on to instantaneous sentence. So, can someone check what's the problem there? I think you guys have difficulty, or Manish, you're able to. So the system is on. So normally it should be on here. It is on. I'll just call the facility staff to come and do this. Hello, I'm coming from D4P1 we have two screens, so I can see, you can set the image only on one screen. This is not coming on the other screen. D4P1 Stop. Okay, thank you. Alright, so next we can move on to the instantaneous center. I will go to the so the theory part is quite simple. So the basis for the instantaneous sentence. All right. Okay. So if you take a single link in rotation. Okay. So we take O2A. Okay. This is in rotation. So we can write the magnitude and direction of the velocity vector for so now we can write velocity of A magnitude is equal to so O2A guys, can you tell me why we can write like this? So velocity A can be written as the magnitude or the length of the link multiplied by the angular velocity. Why we can write? No. Now, point A is rotating, so it has instantaneous center at O2. So, like at any point on this link, so if you want to know velocity of point C, okay, so we can write now O to C, we can take the distance. Okay. So can you tell me again what's how to do? Okay, so because for any point on the link, the instantaneous center is moving. So therefore, you will be able to link the angular variables with the linear variables. Okay. So for example, if you take a simple triangle here, so this is S, this is theta. So let us say this is R. Okay. So we can write this S is equal to R into theta. So basically theta is equal to S over R. Okay. So this is the point fixed. So we can convert now the velocity can be written as R into. So if let us say this point is in rotation, so we'll be able to link this. Okay. So mainly because the point OP is instantaneous center for any point on link on this link. Alright, so therefore we can connect the linear variable to angular variable. S is a linear variable, so theta is a angular variable. So angular displacement, linear displacement. So R is the position. So we can say position vector. So now what I'm going to do is I will take draw point A. Now let us say point B is here. This is your link 3. Link 2. Okay, so now for link point A is common to both link 2 and link 3. So point A is common to link 2 and link 3. But for point A on link 2, okay, for point A on link 2, the instantaneous center is O2. Okay, so for point A on link 2, the instantaneous center is O2. But what is the instantaneous center for point A on link 3? So for point A on link 3, O2 is not the instantaneous center. Okay, so we need to find out the instantaneous center for point A on link 3. So this one we can find out by identifying all the instantaneous centers on the mechanism. So let us say we apply the Kennedy's theorem. So Kennedy's theorem says that 3 links in plane motion will have 3 instantaneous centers, and all the 3 instantaneous centers will lie on a straight line. Okay, so now we know this is instantaneous center 1, 2, and this is instantaneous center 2, 3. Now the instantaneous center for 1, 3 will lie on this line. Okay, so this will be instantaneous center 3 and 4. So this will be instantaneous center for 1 and 4. So there will be another instantaneous center 1, 3 on this line. Okay, so you can join these two, and the intersection point will give us instantaneous center 1 and 3. Okay, so basically 3 links in plane motion will have 3 ICs, and 3 ICs will be on the same line. So 1, 2, 2, 3, 1, 3, all on the same line. 1, 4, 3, 4, 1, 3, all on the same line. So now point A on link 3 will have instantaneous center at 1, 3. So for point A on link 3 will have instantaneous center at 1, 3. So that means now if you know velocity A, we can write O2A into omega 2. So let's say we know omega 2. Okay, so that means you know velocity A. So once you know velocity A, then you can find out angular velocity of link 3, okay, by knowing the instantaneous center for point A on link 3. Okay. So you plot the mechanism to scale, identify all the instantaneous center, measure this distance. Now point A on link 3 will have the instantaneous center here. So since you already know velocity A, okay, so always you know V is R omega, omega is V by R. Okay, so once you know velocity A, so we can calculate angular velocity of link 3. So just by measuring the instantaneous centers. Okay, so similarly if you know from B to instantaneous center 1, 3. Okay, so for B the instantaneous center is O. Okay, so you will be able to calculate velocity B and velocity B to A. So if you know velocity B to A, so velocity B to A will be AB into omega 3. Because omega 3 you will be able to calculate, therefore you know velocity B to A. Okay. So then you will be able to calculate your omega 4 and velocity B from the instantaneous centers. Okay, so the basic idea is you are able to locate instantaneous center for the same point, okay, with respect to two locations. Okay. Okay, next we'll move on to. So the instantaneous center is a point at which the relative motion of the two limbs is purely rotational. Okay. Now when we talk about the number of instantaneous center for a mechanism, so we know it is the number of ICs will be n into n minus 1 over 2. So for a 6-bar linkage mechanism, we will have 15 ICs. And you can identify all the ICs like this. Okay, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. So then 2, 3, 2, 4, 2, 5, 2, 6, 3, 4, 3, 5, 3, 6, and yeah. So these are the 15 possible ICs for a 6-bar linkage mechanism. Now, one of the questions in the end of term exams will be, mechanism will be given, you will be asked to find out all the 15 instantaneous centers. Okay? So make sure you plot with a reasonable scale in the exam. So if you plot too small scale, then you will not be able to locate all the ICs. Okay? So the question will be simple. Locate all the 15 ICs and find out the velocities of 1 or 2 points. And that will easily take 1 hour if you practice, if you know clearly what to do. If you are not sure, then probably you will be wasting a lot of time. Okay, so and that's one of the reasons why you should do your assignment question clearly understanding what you are doing. So if you do your assignment question, clearly you know what you've done, then exam will be just a quick one. Alright, so now let us look into this IC's method. So we know the Kennedy's theorem, right? So three links in plane motion, we have three ICs all on the same line. So now all the pin joints on the mechanism will be the ICs. So you can locate the ICs on a given mechanism by identifying the joints here. Now this is the IC 1, 2. So this is 2, 3 connecting link 2 and link 3. So this is 3 and 4. Okay. This is 1 and 4. Now, so we know 4 ICs, and this is a 4-bar mechanism. So maximum there will be 6 ICs, right? So 4 into 3 over 2. So 6 ICs we need to find them. So 1, 2, 2, 3. So link 1, link 2, link 3. So there will be 3 ICs. Now we know only 2. The third IC will be on this line. So we can plot a line connecting. So we can draw 1, 2, 2, 3. So we draw this dash line. Okay, I'll go back. So this is 1, 4, 3, 4. Okay. So there will be another IC 1, 3 on this line. So connecting 3, 4 and 1, 4. So link these two lines. Now you can see this is 3, 4, 1, 4. So 1, 3 will be on this line. 2, 3, 1, 2. So the intersection point will give you the instantaneous center for link 1 and link 3. Okay, and for link 2, okay, at this point the instantaneous center is moved to 2. Now the same point on any point on link 3, any point on link 3 will have this instantaneous center. For the given orientation. So for the given orientation of link 2, any point on link 3 will have its instantaneous center here. Okay, so since we know velocity of this point, then you are able to fix the angular velocity of this. Okay, so if you know the distance from the point to the instantaneous center, then you can fix the angular velocity of this link. So if you know omega 3, then any point on this link, you can find its velocity. So from instantaneous center, you measure the distance, then multiply with omega 3. That gives you the velocity of any point on the link. Okay. So next we need to plot 1, 4, 1, 2. Okay. So if you take link 1, 2, 4. Okay. So link 1, 4, 1, 2. So there will be 3 ICs. We know 2 ICs, 1, 2 and 1, 4. So 2, 4 will be on this line. So similarly, this is 3, 4, 2, 3. So 2, 4 will be on this line. So the intersection point will give you 2, 4. So 1, 3 we could identify and 2, 4 we could identify. Alright, so all the 6 instantaneous centers we know. Okay, now let us look at this example here. So this example, which is, I think we've done this using the velocity polygons method. Now the same thing we have to do by instantaneous centers. Okay. So first identify 1, 2, 2, 3, 3, 4, and 1, 4. Yeah, guess what's happening? Any question? Okay, so we know 1, 2, 2, 3, 3, 4, and 1, 4. So now you can draw a dotted line here. Okay, 1, 2, 2, 3. So 1, 3 should be on this line. Now you know 1, 4, 3, 4. So 1, 3 should be on this link. a dotted line again on the link itself. Now you can see the instantaneous center for 1 and 3 will be on link 4 in this case. So this is the instantaneous center 1, 3. Okay, so once you know instantaneous center 1, 3, next we try to find out this is 1, 4 and this is 1, 2. So 1, 4, 1, 2, so 2, 4 will be on this link. So 2, 4 will be on this line, dotted line. So similarly, this is 3, 4, 2, 3, so 2, 4 will be connecting this line. So you can locate now instantaneous center 2, 4. So that means we got all the 6 instantaneous centers. So 1, 3 here and 2, 4 here. So now so I think calculation part is once you know velocity of this point, the calculation part is very simple, right? So once you know velocity of this point, okay, so omega 3 you can calculate. How you can calculate? VA over from A to instantaneous center 1. So VA is the velocity on the link to V1. Now this is also point on link 3. Okay, so we use VA and for link 3 on point A on link 3, the instantaneous center is 1, 3. So therefore you measure the distance from A to instantaneous center 1, 3. Okay, so VA over this distance will give you omega 3. So once you know omega 3, then you can calculate velocity VA, then you can calculate angular velocity of link 4. Okay, then velocity of all the points. Alright, so any questions on this so far? Okay, for the Sunday exam, you know the time already.
Huh? I forget, I don't know what exam on Sunday.
Got the AC quiz and also this exam and also the sub quiz. Yeah.
I think I do already, I did
No,
already. I don't want to
the AC quiz on Sunday also. The 3 question one,
Okay.
the multiple
Can
choice
you
one.
just show you? Can you try to do this?
Yeah, that I really should. Sunday one is assignment handout.
Okay,
And
so you will be given
class
a
test.
mechanism something like this. Okay, so you need to plot the mechanism to scale.
51.
You are going to do now here. Okay, you may note down. Okay, so the questions will be like this. So plot the mechanism to scale. Then determine all instantaneous centers. So you will be given a simple 4-bar mechanism. Okay, then you have to determine the velocity of the point by IC's method and also by graphical method. So velocity of a point you need to calculate, you need to do by both methods. So there are 4 aspects. So each aspect you will have 12 marks. All correct, you will get 10 marks. Okay, it's a simple 4-bar mechanism. Now, you may note down this. Can you do this now? It will take maximum 20 half hour maximum. And do it on paper. Okay, so in the online classes, you are going to on paper, scan, and upload.
People.
Okay, so you are not allowed to use any software. So you can only do the simulations using the software with assignment. Okay, so draw the mechanism to scale first. Yeah, class test is online. Sunday. Only one question.
Only one question.
Ah, sorry.
So in this case, we follow the MM1, is it?
Either way, because both the dimensions are different.
The quiz will give inch.
So whichever way you want, you can use the dimensions.
I mean, but we can use like inches, then just use as mm also cannot. Must be this scale. Like example, 5 inches, I just change the 5 to instead of inches. Is it okay or?
Or you want to use 5 number and 8.86 number.
Yeah.
So your answers will be inch per second. You can still use.
Okay.
If you use your answer will be per second. Given, because 127 is a big number, so you can play with it. So if you want to choose a scale, you can choose 1:10, then you use 12.7. So no, it's up to you, whichever the unit you want to use.
What's that? It's 12 cm.
22.5 cm. If I will not long enough.
0.10. 100.
Okay, in the exam, you need to use the dimensions correctly, units correctly. When you write velocities, you must write whether the unit is inch per second or mm per second.
Sliding.
Okay, first question is draw the mechanism to scale and determine all ICs and velocity at point B, both by ICs method and polygon method. So that means you need to draw a velocity polygon also. Okay, this was one of the questions few years back. So you can have a similar, something very similar. just follow the same step.
Wow, my hand draws so hard. Bye bye. So my dear hundred.不相信。哇，下下人家也爬山。First, I want to.
That is happy. So make sure 1, 2, 3, 1, 2, 3, 4 is there. All 6. So we can see here ground is there, 4 is also there. Okay, and here the motion is. So the instrument you cannot have instrument center for parallel. So therefore we choose that instrument So this is like this. This is what I refer to as part B. So part C defines the velocity of point A by this method. So the velocity of point B is this height. So how you can find the velocity of this point by using instantaneous method. So this is the instantaneous method for this. So you multiply B. So before that you need to find out angular velocity of the method. So this one
I'll show you. Three, four, 四个丢是吧？四个丢可以 fail。
Show all the ICs. So use appropriate scale. Yeah. So you can also take 1/4. So 1/4, 1/4, so 1/4 is 3/4. 3/4. You are Takashi.
Left is 1/4, right? This is 1/4, so 1/4 also again.
做个出来，这个 point 画这个 length。Finish already. I finished finding it. Cannot find it. I said forget the one can move. One can move.
So you were at B. Okay, show all ICs. You need to show like this. All our ICs.
Anyone one, two,
Again? 1 to 4 you need to show here, you need to show.
Oh, I think the two 是 the two infinities.
Yeah, it's either left or right.
Then this is up again. 这个 move out
Yeah.
to fit.
I
I
think.
thought my one is 1, 2, and 2 for that. That's why it's
Oh. Yeah.
So for example, if you are taking inches, 127 mm into 1. Velocity A is 127 mm per second. Because omega 2 is given as 1 radian per second, right? So then you can calculate omega 3. So you can calculate omega 3 from VA over A I13. VA is simply O2A into omega 2. Omega 2 is given 1 reading per second. So O2A is given 127 mm. So 127 mm into 1. So 127 mm per second. So omega 3 you can calculate as VA over A instantaneous center to 1. So you can also calculate velocity B. So once you know omega 3, you can calculate velocity B. So for B on link 3, instantaneous center is from B to instantaneous center 1, 3. So from B to instantaneous center 1, 3 multiplied by omega 3. So that gives velocity of B.
So can you repeat? Can you repeat?
Velocity B will be this is by IC's method, instantaneous interest method.
Sounds easy.
Omega 3, right? So A instantaneous 1 to 3 is from one 3 to A, right?
A to here.
Okay.
Can take B 1 3.
Yeah, from A to 1 3.
Can take the top.
So if we scale the do we do the conversion and
Before.
oh, before?
No, whatever is this length, right?
The same as the scale up.
Yeah.
So you have to do it before we start.
No, the calculation will be just you add here. VA will be as it is. No change. Omega 3 VA over A instantaneous center 1 3. So what is this distance? If you are using 1:1, you can use as it is. If you are using 1:5, then you need to convert into original scale, right? So this is the solution for question 1, question 2, question 3. Now question 4, you have to do the velocity by polygons method. So you know now the velocity A will be, so the direction of angular velocity is given like this. Okay, so omega to VA will be perpendicular like this. So this is the direction of velocity. So you know both magnitude and direction, VA. Then velocity B to A. So velocity B to A will be like this. So B to A will be the direction of. Okay, this is velocity B. This is velocity B. The slider can go up or go down. Then velocity B to A will be perpendicular to link BA. So it will be like this.
So the direction for VBA is both.
This one is link AB, right? So perpendicular to the link.
Both directions.
It can be, we don't know. Once you plot the velocity polygon, you can fix the direction. Slider can only go up and down, right? It is constrained. Then you need to draw the polygon. So your velocity A will be something like this. Okay. So velocity B to A will be like this. Okay. And velocity B will be like this. So now this will be velocity B. So your velocity polygon will look like this.
So by the exam, are we supposed to draw on the velocity polygon on the main drawing or another
Another one.
one? So I just draw XY with the same angling.
So you answer part A, you show the diagram, okay, graphical drawing. Part B, you show all the instantaneous center. Part C, you show only the calculation. Okay. Part 4, you draw the velocity polygon.
Okay.
It's up to you.
Can use the same.
If you want, you can use the same one, but you need to show your velocity B calculation. And you need to show the direction. Anybody calculated, I think
So
someone.
the omega 3.
You tell me.
My omega 3 is 1.32 mm or 5.2 inch. Also, yeah, okay. Then my calculation
Which one?
W3 是260，不是260 mm。
Again, it's 1
mm per second。诶，sorry，不是，wait a second，哦，W3 是0.488。
Scale in the same way.
W3 488. My velocity I calculate is my velocity is the length I measure is 260 mm. I forgot lah. So I 2.6 cm lah. So I done 100.
One is 291.
291.
Not very clear because I draw a lot of lines.
I divided by 100.
Oh, mine is this thing.
I don't know.
That times 100 gram.
Mine is not the
Is it roughly half less than? It should be less than.
No, VB should both ways should match.
2000 words.
It should match.
Yes, yes. You also do velocity polygon, then both values should be the same. Yes, Johnny, any question? Huh? How much? You see, one way you can confirm yourself is VB by both the methods should be equal, very close.
It's the same because it's 45 degrees, is it?
No, because you are doing instantaneous centers method and velocity polygon, right? So both values should match.
Right.
Yes.
So my measure right is when I get 2.4 is 1.2 and 1.4, right? So why not is 1.2, 1.2 and 1.4 here, and 3.2.3 and 3.4. So should it be like that instead of
3 instantaneous centers, right?
yeah.
Where is 3 instantaneous centers? Because you are doing instantaneous centers for 1, 2 and 4. I link 1, 2 and 4.
1, 2, 3, 4. 1, 2, 4. Here lah. Right?
1 is your ground link, 1 is also here, this is the ground link, this is also ground link.
So why not is 1, 2 and 1, 4?
How?
Why not 1, 2 and 1, 4 like that?
1, 4 is at infinity,
Infinity. So infinity is this way or
perpendicular to this link, ground link.
this thing? Oh, so it doesn't measure. Okay, there.
Anybody got velocity B for both the methods?
Just take my kids here.
Yes. Okay, so this is the simplest question possible.
We'll go ahead and it's not easy. 3, 5, 3, 4.
No, if you seriously plot, then I think it will not take much time. Yeah. So first time it will take time. And this question you will have maximum 1 hour, so you have to do all parts.
1 hour.这个是我的博士，这 test 这个，所以他们放小了这样。
Graduation. Oh, 10%. No, it is listed on 1 point because it is quiz. So, but this, the weightage is 10 marks. Right. So 40% for the assignment, 10% for the class test, and 50% for the electronic. Anyone giving me the value for velocity B? By both the methods? Okay, anyone not clearly understood, let me know. I can draw again and show you.
Yes, please.
Say again. So your part A is something like this. Okay, so part A just plot like this. So part B will be So your card B looks something like this.
Oh, I mean 也可以啊，他们没有讲不可以。
So this is part C. So part D will be your velocity polygon.
I'll draw three separate graphs. I'll draw all separately. Is it during
It's
the
up to you. I want to see all the instantaneous centers. I want to see your velocity polygon. I want to see your calculations. So this is your velocity A. Okay, B to A is perpendicular to. Now this is your velocity B. The intersection point is Q. So this is as I showed here. So you can, from this velocity polygon, you can measure the velocity B, then compare this with your instantaneous centers method. So I'll be happy if anybody can give me the values.
130. I got two different answers.
How different?
127.44 and 130.
They are very close.
我没有做到。
They are acceptable.
但是也没做。
Alright, so don't expect you will be getting exactly the same, but something similar. It may not be the same. Okay, so but normally it takes only 35 to 40 minutes to complete it seriously if you are doing it. Okay, so online you need to answer the marking scheme is very clear. So you will have
It's right down, so I will shape this out.
okay, so there are 4 parts you can see here.
Actually, don't know.
So plot the mechanism to scale will be 2.5 marks. Then determine all ICs 2.5 marks. Determine velocity of point B 2.5 marks by ICs method. Then find velocity B by graphical method. So total 10% weightage. Alright, so guys, you can go for a break now, 8:55. So come back by 9:00.
You draw, you do a calculation, you draw first, you draw before the AutoCAD first. Then you get all the answer, you just convert it to paper. So paper, you just draw accordingly to the line carefully.
But imagine the go manager, because every time we draw then we're sagging a bit.
Yeah, so you draw the AutoCAD first, you get, then you calculate all the dimensional, and just convert everything not convert,
Oh, and you have your like all the dimension already, you just draw.
hand draw all for the dimension.
Yeah, that's true.
The velocity element really it's just basically for example it's like that, right? You're gonna do A is perpendicular, right? A perpendicular right? Then you find your axis, your origin. Then you see just from here
Just draw all
swing over
over.
I don't know how to
Use the ruler. Actually, you just yeah, I do that.
then bring over horizontal like that.
Yeah.
Then you draw your point. Okay, is it?
Yeah.
Okay, now let's try it.
But then you have to be within this yeah, with this like if you draw too big your thing not long enough then jialat already. When you finish your IC, I finish the calculation, but I don't put it on the board.
Oh, I calculation.
This is
Actually, I haven't finished calculation. Just I really talk to him, I got feeling that these 4, 5, 5, 6 hours actually shouldn't be inside.
No, I think sure have one. Sure have one. Because I checked the. I mean, his drawing that one maybe a bit long.
Just missing one, maybe the triangle also.
You screenshot your cursor inside.
But I did until. So I left the calculation part already. After I'm done.
Oh, wow, that one the report.
I just started with it. So I don't know after the break then I find him. Maybe I can find do this. So the exam is 4 link or 6 link, the test.
I think he says.
Why is it perpendicular? Always perpendicular.
which one?
For this case, the VB.
6 very long.
BB. So BA is perpendicular to the lane AB.
Oh, just finish measuring.